So in this video, we're going to talk about the central limit theorem. This theorem, extremely important in statistics, all right? The foundation for inferential statistics is formed by the central limit theorem. We're going to abbreviate the central limit theorem with CLT. We're going to use this so much. In fact, we're pretty much going to use this for every problem for the rest of the course. All right, there might be a couple where we don't use it, but this assumption is crucial for inferential statistics. This describes a relationship between the sampling distribution of sample means and the original population that the samples are taken from. Okay, so if a random sample of n greater than or equal to 30 is drawn from any population with a mean mu and standard deviation sigma, then the sampling distribution of sample means x bar approximates a normal distribution with mean of the x bars, sample means, equal to mu, and standard deviation of the sample means equal to sigma divided by the square root of n. Okay? So to show you in a picture what this means is, say I take a distribution, so this could be any distribution, any population distribution, no characteristics on it whatsoever. So these are coming from x values, right? And it has some mean mu and a standard deviation of sigma, okay? From that population, if my random samples are drawn n greater than or equal to 30, what does that tell me? Then the distribution of sample means, where n is greater than or equal to 30, is going to look like this. It's going to have a mean of sample means equal to mu and a standard deviation sigma sub x bar equal to sigma divided by the square root of n, where the values here are x bar, sample means. So this is the distribution of values. This is the distribution of sample means. So any population, as long as n is greater than or equal to 30, is going to be approximately normal with a mean mu and a standard deviation sigma divided by the square root of n. That's what the central limit theorem promises. It tells us about the averages. It doesn't tell us anything about the original data, but it says that if I take the averages, then the distribution of the sample means, the averages, are normally distributed. Okay? Very powerful. All right? That's option one. So option one, n is greater than or equal to 30. The other option, or, okay, if a random sample of size n are drawn from a population that is normally distributed, this is the other option, normally distributed, then the sampling distribution of sample means is normally distributed for any sample size n. So it doesn't matter if n equals 5 or 25 or 50. It doesn't matter on the size. If we know that n is normally distributed, the population is normally distributed, then I don't have to have some limit of n greater than or equal to 30. So what is this saying? In order to use the central limit theorem, I either need to have n greater than or equal to 30, or I need to have normally distributed. Now, could I have both? Sure, I could have both, but I only need to have at least one of these is true. So at least one, that's what or means. At least one of these is true. Either n is greater than or equal to 30, or the population is normally distributed, or both could be true. Okay? So if the population is normally distributed, meaning I have some population and I know it comes from a normal distribution, so the normal population distribution, then when and it has some mu here and some sigma for my standard deviation, then whenever I take sample means, so the distribution of sample means here for any n, okay, that is going to be still a normal distribution where the mean of the sample means is the mean and the standard deviation of the sample means is the standard deviation over the square root of n. Okay? So here's my two options. All right? I either need to be drawing n greater than or equal to 30, and then it doesn't matter what my population looks like. It can be the weirdest looking population, whatever. But if I draw greater than or equal to 30, then my values, if I take the averages of that sample, so say I pick out, 30 or more x values, and I take the average of those x values, right? Then and I do that over and over and over and over, and I develop some sample mean distribution. So x bar 1, x bar 2, for x bar 3, x bar 4, so on, for as many sample means as I need to form my distribution here. Then if n is greater than or equal to 30, that's normally distributed, and therefore we can use our table to find the probability. That's what's so powerful about this. I can take any data set, okay, and if I look at the averages, the means of those data values, and I can form a sampling distribution from the sample means, and therefore I can apply the normal curve table to that to figure out probabilities. Very powerful. This is the engine that drives inferential statistics. Without the central limit theorem, you would not have any of the statistics that we have today. So this is probably the most important theorem of the entire class. Okay, so we're taking data values and from that creating a sampling distribution of sample means, and ultimately that distribution becomes normal. Okay, so either it has to start from a normal population and then it will still be a normal population, or if it's some weird population or you don't know what the population is, because that's the case most of the time in the real world application, okay, then if you take n large enough, then you can assume that it's approximately normal and get a close enough probability for whatever you're trying to do. Okay, so that's the power in statistics. All right, so as the sample size n increases, so as n goes to infinity, so we get larger and larger samples. So there we had a restriction n greater than or equal to 30. It's approximately normal. So if I get larger and larger samples, like n equal to 1,000 or 10,000 or whatever, the sampling distribution becomes more and more mound-shaped, and it eventually, if n goes to infinity, this will eventually be exactly normal. But since we can't reach infinity, we're not going to go out and get infinite amount of data. Then all we do, we approximate the normal. So the bigger your n is, the more and more it looks like the true normal curve. Okay? So as n approaches infinity, what happens to the standard deviation of the sample means? Remember, the standard deviation of the sample means is the standard error, right? So how is this defined? It's the standard deviation divided by the square root of n. Well, what's happening as n gets really big? Well, let's think about it. If n, so say you have a number and it's like, sigma divided by, and maybe n is equal to 25. Well, if I take the square root of 25, I get 5. Square root, so sigma divided by 5, okay? But say n is like, I don't know, maybe it's 100 now. So now it's sigma divided by the square root of 100, so it's increasing, right? So now it's sigma divided by 10. Which one is bigger? Well, let's think about it. If sigma is like 20, so 20 divided by 5 gets me 4. Here, 20 divided by 10 gets me 2. What's happening? As n gets bigger, the value of the standard error gets smaller, right? So this is getting smaller. It gets smaller. Smaller as n gets larger. Okay? As n gets larger. Right? Now, what about the mean of sample means? What happens as n gets larger here? Well, the mean of sample means is still just equal to the mean. There's no dividing by square root of n or anything like there was in the sample standard, or in the standard deviation of the sample means. So this mean, the average, remains unchanged. Okay, so as n increases, the standard deviation gets smaller, but the mean stays the same. Okay? And how I want you to think about this, why this intuitively makes sense, okay? Think of n as the amount of information you have. So n, like say we go out and we ask 30 people, what do you think about ice cream? Do you like it? Yes or no kind of thing, right? So that's going to get some good estimate on the public opinion of ice cream in Angelina County. But if we go out and we ask 10,000 people, we're going to have a more true understanding of what people's opinions are in Lufkin about ice cream, whether they like it or not. Okay, maybe this, produced like a 82% rate at 30. But if we went out and we asked 10,000 people, maybe it was like 74, 3-2, right? So maybe 74% of people truly like ice cream versus don't like it, all right, in Angelina County. Whatever, I'm just making this up, right? So the idea here is, excuse me, the idea is the more information we go out and gather, the more knowledge we have. Therefore, our chance of making the wrong decision, our error, decreases, okay? And you think of the standard deviation of the sample means as the standard error of the mean. So how far off we are from the mean. Well, if I have a whole lot of knowledge, the chances of me making a mistake are smaller than when I'm working with less knowledge, okay? Therefore, as my n increases, my error decreases. That's how I want you to intuitively think about this, all right? So big theorem here. Central limit theorem, like I said, it's the most important theorem in all of statistics. Without it, we would be done for the rest of the class because, there's just nothing we can do. All right, this is the ABCs statistics right here. Central limit theorem. Key thing to walk away with is this. In order to use this powerful tool, we either have n greater than or equal 30, or we're told that the population is normally distributed. And if we don't have one of those two things, then we can't use this powerful theorem.